Okay, so yes, first I have to thank the organizer for inviting me to this very nice conference. So, as I understand, the topic of my talk is a bit different from most of the talks here, and the reason being that not many talks are concerning non-equilibrium. So this will be about non-equilibrium properties, but I will strictly keep to one-dimensional systems. So it will be about non-equilibrium. It will be about open systems and driven and quantum chains. So it will be 1D. So I'll make a short menu for what I'm going to speak about today. Essentially, I mean, okay, I put this title, walking graph states, just kind of to provoke the attention, but essentially I'm speaking about three types of exact solutions which I can put under a common frame. And the common frame is this concept of a walking graph state, which I'll try to introduce. But essentially I'll do it on the case of several examples. And so there are three cases, exactly solvable cases. Case one will be the very famous spin 1/2 XXZ chain. So the anisotropic Heisenberg model, about which we know very much, but still I claim that there are some interesting things to be learned when you drive the system out of equilibrium. Second model is the Fermi-Hubbard model. So Fermi-Hubbard chain. And the third model is a very recent work, which has been just published in Nuclear Physics B, is the Lie-Sutherland spin 1 chain. Spin 1 chain. So before I forget, let me just give you a few references on this. I mean, maybe I will not be able to cover everything, but this is the main course, and these two things are desserts, which I might not be able to get there, but you will somehow, I hope you get the idea when I describe the XXZ case. But I just want to claim from the beginning that there is a common frame under which you can put also these two other models, even though much less is understood about the structure of the solution here. So the only thing which is common is this structure of the graph state, of the walking graph state. So let me just give you briefly the main references. So this is PRL 6. And then there is Hubbard, is PRL this year, 112, 0306, 03. And this is Nuclear Physics B, 88245. Okay, so let's start with case one. Okay, let me just start with a picture, a scheme of the setup. So what I'm going to consider is a quantum chain. So it's not a tensor network yet, but I will try to connect to the topic of the workshop. So there will be a little bit of tensor networks, not much. I mean, everything is more or less MPS. But just to somehow make some advertisement why this should be still of some interest, this MPS will have infinite bond dimensions. So just to try to make some pre-interpretation of what I'm going to say. I mean, the graph comes from trying to get the connectivity in this infinite dimensional ancilla space. So, but let me just go slowly into this. So let's just take a quantum chain, which is a chain of quantum particles, be it spins 1/2 fermions. So finite level quantum systems. You can think of quantum spin systems. And then you couple it to some external reservoirs. Yeah. So the idea is to have an open quantum system, but there is also, I mean, you may think of, okay, I mean, why, you know, this is a dissipative quantum system. This is a driven dissipative quantum system. But the way I want to couple it to the outside world is really as benign as I can think of. So I don't want to destroy the coherent character of the many-body dynamics here. I mean, at least I don't want to, I try to affect it as little as possible. So I just couple it to the outside world locally. So I'll take, let's say, Limblad operators, which will be acting ultra-locally on the degrees of freedom at the boundaries of the system. So let me just, you know, just immediately start to discuss case one, which is the XXZ chain, you know very well. So I'll just, you know, repeat the Hamiltonian. So I will denote the system size by little n. And this will be the generator of the unitary dynamics in the bulk of the system. And then I will produce jump operators, which affect, as I say, only local degrees of freedom near the boundaries of the chain, which will try to, which will produce incoherent processes, right? This is the coherent part, and the incoherent part is generated by 4 Limblad operators, which in this XXZ case could be simply for example, sigma plus, sigma minus at the left end, or sigma plus and sigma minus at the right end. And these constants, A, B, C, and D, are positive real numbers, which can be interpreted as rates. So now this is where the quantum world meets classical world. I mean, this is a hybrid system. It is, I mean, it is a Hamiltonian coherent dynamics in the bulk, and there is a kind of constant monitoring of the system by the environment locally at the boundaries. Okay, then you can, okay, I don't want to enter into the discussion of how one derives these dynamics. Of course, you know, I mean, I guess in this still this type of community, I don't have to discuss introducing the Limblad equation, although I could. I mean, if there is maybe, I don't know, but still, I mean, let me just go straight to the evolution equation. So what I'm going to consider is the evolution equation for the density matrix, which has, as I say, 2 parts. It is the unitary part plus the dissipator. I will write superoperators with the heads. So this is a linear machine which takes density matrix and spits out an operator. This is not a derivative of density matrix. So this is simply this is the anticommutator, yeah? So this is the Limblad equation. Take Limblad dynamics. This is the Markovian master equation, which describes the evolution of the system. So now you may wonder whether, taking a system for which you know that there is a big bulk of literature about equilibrium, ground state, it's a spectrum, thermodynamics, and so on, which is covered essentially by techniques which are known as quantum inverse scattering and algebraic data ansatz. So if you take such a model and you couple it to the outside world by some incoherent processes, then you may wonder whether there exist exact solutions for the steady state, and whether these exact solutions tell you something new about the dynamics of the model. I try to argue that both answers to both of these questions are positive. So I'll try to be as precise as I can be in such a lecture for the first part. Then the desserts I will give you just briefly, I guess, because 1 hour is not enough. But anyway, let me just... So what I'm going to do is I consider a non-equilibrium steady state, which is defined as a limit. Sorry, I will write it as rho infinity, which is the limit to infinity of this dynamics. Yeah, it's a fixed point. Sorry, it's a fixed point. So this is clearly the fixed point of the Ljubljana operator. Yeah? So this guy satisfies the steady state Limlat equation, which is commutator with the Hamiltonian should be equal to the dissipator on this operator. So this is the equation of motion for the steady state, which we are trying to solve. Okay, so and now, okay, now I'll try to, I'll have to probably buy some of the statements I'm going to make, but still, I'll try to connect to the, even though this is not the way this has been derived. This has been derived in a bit of school way, but what has been the progress of the last, let's say, last year was that we were able to, mainly in the, I forgot to mention the co-authors, but these papers have been done, 2 of them have been done in collaboration with my graduate student, Ilievsky. So what we have realized with Ilievsky was that actually this has been, that this exact solution can be put under the frame of Young-Baxter equations. And I think we will learn more about algebraic beta ansatz, Professor Skorepin's talk tomorrow. But still, I'll try to write you a Lax matrix, which you will be able then to connect to the standard Lax matrix of algebraic beta ansatz. So let me just tell you 2 proof. Okay, yes.
Before that, so just going back to the physics part. So, are you this, for instance, the 2 first Hamiltonians preserve particle number?
Right.
Is that are we assuming something about the rate? Is there a particle? Is there a fixed particle number?
Right. That's a good point. Yes. There should be a conserved quantity. In this case, it's a magnetization. In this case, a particle number. In this case, also, in this case also there is a conserved quantity. The way I produce the noise coupling to the environment is that I will conserve number of particles of one species. There are 3 species. This is spin 1/2 model. This is spin 1 model. There are 3 species of particles. It's a 3-color model. And I will conserve, let's say, red color. And the reservoirs will produce incoherent change of blue to green and green to blue. So there will be always a conserved quantity.
In the Hamiltonian part.
In the Hamiltonian part. And the action of the Limlat operators will be to change this conserved quantity from, let's say, by +1 or -1. So yeah, that's a good thing to add.
It's gone. The system does not preserve.
Right. The open system does not preserve it, but the bar preserve it. So it makes sense to study. But that's a very good question you ask, because that's exactly the idea. Why? This is a physical motivation. Why you want to study this model is because you want to study states with currents, because these are states which produce currents, and this is paradigm of non-equilibrium physics, right? To understand non-equilibrium states with currents. Yeah? And then you may want to connect this to what linear response teaches you, or you want to go far away from linear response. Both connections can be made. But okay, that's probably going beyond this talk. But it's very good. Thanks for the question. Yeah, because it definitely is a part of motivation for why one should be interested to study this. Okay. So let me just So 2 things, two sort of remarkable properties of this steady state density matrix can be made, which are universal, which essentially are true for all 3 models. The first, so the observations. Rho infinity, that is steady state density operator, can be factorized into square root, into non-Hermitian square root, which is, I will call it an S operator, and I will put explicitly the dependence on the system size. So S of n will be an operator which lives in 2 to the n by 2 to the n dimensional Hilbert space, in physical Hilbert space, and the density matrix will be written as such. Of course, this is nothing. You say, okay, or any positive operator can be written in this form, but there will be more to it. This will be what I claim, which is known in linear algebra, a Cholesky decomposition. Cholesky decomposition, meaning that this guy S is an upper triangular matrix in a computational basis. This comes from particular property of the representation of SU2. There is a SU2 group behind, and there are non-unitary representations of SU2, but which one has to consider. And the fact that I have to use highest weight representations of SU2 immediately implies, as you will see. I try to stress this point again, but this is kind of important. At least it seems important for me at the moment, because I can only understand fully the structure of solution for this model. For these 2 models, the structure is not completely understood. There is no corresponding Young-Baxter equation yet for these 2 models. As you know, for example, for the Hubbard model, there is this Shastri's R matrix, but it's not really, it doesn't really have the universality of of the SU2R matrix. So so it's a bit. I mean, there are things to be discussed, and yeah. But anyway, let me just go straight to this solution. So this is the first observation. The first observation, there is a Koleski factorization, and then the rest is, this is like density matrix. I mean, this is again a naive, let's say, naive pedestrian's interpretation of what we are doing. I mean, this is density matrix. Density matrix is about probabilities, but in quantum mechanics we work with probability amplitudes. So first you factorize density matrix, to have an object which describes probability amplitudes, and then we shall discuss what this object does. And then this object, Sn, admits a nice matrix product representation. So there is an MPO ansatz for the square root of density matrix. So there are some indices, S1 to Sn. You start from a state which I call 0. Now you are in Ancilla space, so these are Ancilla operators. This is not a trace, you see? This is not a trace, but you start from some left state, and then you take a product of matrices. You end up in the right state. And then you have a tensor product of Pauli matrices. Yeah. Okay. So this is an ansatz, yeah? You know that always you can write such ansatz, and for exponentially large Ancilla space, you can always write any state as an MPO. Now the question is, what is the property of these guys here, these matrices? First remarkable observation is that these indices only run over Pauli matrices plus, minus, and 0. So I take a complete basis of Pauli matrices, sigma plus, sigma minus, sigma z, and sigma 0. Now this guy is forbidden. This guy doesn't enter into the ansatz. So how come? Well, I mean, first, this was sort of the idea of how one derives and how one derives this solution. But as I say now, it sounds a bit obscure having this connection to the Lax matrices of the integrability. So it's better maybe to explain this in terms of the Lax matrix. So. Yeah. But anyway, before going into that, let me just sketch, that how does this imply that there is a tensor network behind the density matrix? Yeah. This, this S operator, I will write as an MPS. Yeah. It's an MPO. So this double index, double line I will use to denote an infinitely dimensional bond space. So as I say, the representation space or the Ancilla space should be infinitely dimensional, as will become clear in a minute. So, and then you start from a state 0, which is, you can call a ground state or a highest weight state, and then this is the S, yeah? So this is A, and so on. And then this is one S. Then you have to multiply with S dagger, and S dagger is a similar beast, but you do, and you contract, of course. This is multiplication of operators. So this is the bra of the first, the ket of the second, the bra of the second, the ket of the second, and so on. So you contract along this, and here you have to put the if you want, the adjoint matrices A bar. Yeah? The complex conjugate matrices A bar. So if you want, at the end of the day, we will have this tensor ladder structure of the non-equilibrium steady state. But I claim, you can learn everything about a system by just looking at one leg of this ladder. Yeah? So, and then, how does one prove or construct such a solution? Sort of the proof, or better to say, the construction of this matrix A follows from these observations. Namely, it's sort of easy to observe that this ansatz solves the fixed point condition for the Niblat equation if and only if the square root, that is Sn, has the following property. You see, this is kind of funny equation, right? it tells you that the commutator of the Hamiltonian with this operator has to be something which is connected to this operator for a system of size n-1, attaching some trivial operator, which in this case is sigma z, which has to do with the number of particles, namely this is the, say, one excitation, at the left or at the right. Yeah? And this epsilon, okay, I forgot to say what is epsilon. There is something which I forgot to say, namely, I consider now a special case of driving where I put a driving parameter A to epsilon, I put B to 0, I put C to 0, and I put D to epsilon. Which means I have the strongest possible driving where I only inject spin up excitations on the left, and I only, let's say, inject spin down excitations on the right. Or I only flip up spins on the left and I only flip down excitations on the right. With some rates which are, for convenience, equal. They don't have to be equal. I mean, there could be asymmetric rates. One can still write exact solution. But the simplest, let's say, the most symmetric exact solution happens if the rates are equal. So this epsilon is a parameter, is one of the main parameters in the game, which is the strength of coupling to the environment.
Sigma z acts in which space?
Sigma z is the, okay, so this is in physical space. So this operator is 2 to the n by 2. This is 2 to the n-1 times 2 to the n-1. So this is 2 by 2. So this is a spin space, spin 1/2 space.
In one specific lattice side?
One specific lattice side. This is first lattice side, this is the rest. This is the last lattice side. Yeah. Okay. Okay, so this is, I mean, the first point to understand this solution is to understand that the Lindblad equation is equivalent to this equation for the steady state. Yeah? And then the second step is to see that this follows immediately from a solution of Young-Baxter equation for the so-called Lax matrix, which is the solution of Young-Baxter equation in representation in representation which is the product of fundamental representation and an arbitrary spin. And this spin can be any complex number. So there is this Lax matrix, which can be written as a 2 by 2 matrix, which you can write, for example, from Professor Korepin's book. It is, but one thing you have to be careful. There's one crucial modification from what is written in standard textbooks in algebraic beta ansatz for the equilibrium systems. Namely, you have to allow this auxiliary degree of freedom to be arbitrary spin. So this matrix is now, this matrix has two legs. In one leg, it belongs to a spin 1/2, and in the second leg, it belongs to the elements. So this is 2 by 2 matrix. This is a physical space 2 by 2 matrix, and its elements are infinitely dimensional matrices, which are connected to these operators S plus, S minus, and SZ.
Phi is the spectral parameter?
Phi is the spectral parameter, yes. And gamma is related to anisotropy, which is cosine gamma. I use more or less standard notation. But phi is the spectral parameter, yes, which I will use to manipulate the solution. Okay, so now, what is these guys here? These are, okay, there is a parameter, a little s. Yeah? This is, as I say, this is little s. I'm sorry for my ugly writing. But little s, as I say, is a free complex parameter. I should not fix it anymore. I should not fix it yet. So, so there are 3 operators, which are the generators of the so-called quantum group. UQSL2, and can be represented for any S. And you may, well, this is Q could be related again to parameter gamma. Q is I to the I gamma, so this is this trigonometric deformation, if you want. And then these operators SZ are 3 diagonal matrices. So there is an ancilla space which is infinitely dimensional. I will write them in this trigonometric way. So in terms of trigonometric functions of the parameters of the model. minus S. And then you see there is this spin parameter coming into two parts of the guys. So these are three diagonal operators. These are angular momentum. Essentially, this is deformed angular momentum. And there is a special state which you call highest weight state, which is this zero state, which has this property that if you try to raise the spin, you cannot do it. It's annihilated. And if you take the projection of the spin on this state, you get this little s times this state. So little s could be considered as angular momentum. And then if you apply S minus, you get a series which never terminates in principle. So you have an infinity dimensional representation of essentially this is SU2 if Q is equal to 1, but it's also deformed SU2. So it's the quantum symmetry of the XXZ chain. Okay, but the point is now here it's kind of, this is a non-unitary representation. I mean, this is, there are unitary representations and people have mostly used I would say, in my interpretation of the business, in equilibrium physics, people would mostly use unitary representations. But here, it's necessary to use non-unitary representations of this Lie group or of the quantum group, which is the symmetry of the model. And okay, so how does then this MPO happen? I mean, maybe this will be connected to what, as I say, what Professor Kurepin has to say tomorrow, because this will be again generating matrix product states from solutions of Young-Baxter's equations. But in this case, the only difference will be that these matrices will have infinite bond dimension, because this has to do with this infinite dimensionality of this ancilla space. Yeah? Okay, so let me just conclude this connection. So now the statement is, which is very easy to prove. The statement is the following. I mean, introducing the Lax matrix, we realize the following, that this square root of the density matrix can be written as the highest weight expectation value, or if you want, ground state expectation value of this guy, where you put a representation spectral parameter to pi over 2 S, and then you take tensor product in spin space. I mean, by this index S, I mean I take tensor product in spin space, because this matrix has two spaces. There is a spin space, 2 by 2, two-dimensional spin space, and infinite dimensional ancilla space. You take tensor product in spin space, and of course this is a normal product in ancilla space, so it's like, and then you take expectation value. And and to see that, I mean, that's sort of, okay, and then, there is a connection. I mean, to see that this solves, now the claim is, this solves this defining equation for the square root, which, where was it? It's here. So this solves this equation if there is a connection between the dissipation parameter, or the coupling to the environment, and the spin representation parameter. So you see, there is an I here. So which means that spin representation parameter has to be completely imaginary. So, and it's connected to the noise strength. So, so the idea is that, okay, noise now affects the strength of the noise, or the strength of the coupling, or the strength of the driving tells you what representation of what non-unitary representation of the UQSU2 you should use to produce the MPO for the steady state. And to see that, I mean, this is really kind of obvious. I mean, this, the fact that this solves this equation simply follows from the local, essentially from the Young-Baxter equation. Written on the product space fundamental times this complex spin. If you write local form of this Young-Baxter equation, namely if you derive with respect to the spectral parameter, then you get simply the Hamiltonian, the Hamiltonian density. If I call this a Hamiltonian density, It's a two-body operator. Then this is this Hamiltonian commutator with L. This is tensor product in spin space. L cross L is simply 2 times sine gamma L cross. This is derivative with respect to spectral parameter. So this is simply the Young-Baxter equation. But you see, this is also a kind of operator divergence condition. This is the time derivative of that sort of a two-side operator, which is given in terms of some sort of divergence. Yeah? So if you simply tensor product this, you make a tensor product of this guy from the left and from the right by appropriate powers, and then sum up, and take the sandwich between 0, 0, then you exactly get this kind of state. And this tells you that, on the left-hand side you will get, on the left-hand side you will get this, on the right-hand side you will get precisely this, for this particular choice of epsilon. So this is the way you can now show that this is exactly the solution. Now, okay, this was a bit, how am I doing the time? Okay, so it's okay. So this was maybe a bit technical, but let me try to conclude. Let me try to give you a pictorial interpretation of what we have done. So let me go to this concept which I advocated in the title, the concept of a graph. So, this representation space is a bit, it's quite trivial, but still not completely. So let's try to describe what this matrix product is doing, because these are infinitely dimensional matrices. We can describe this in terms of simpler objects. These are infinitely dimensional matrices, but they are acting as 3 diagonal operators. So which means that these 3 diagonal operators now, which enter, let me just now to write out these operators. These operators simply can be written out from here, putting spectral parameter to be pi over 2. You get A0 simply to be a cosine of diagonal matrix, which is again a diagonal matrix, which I can write so as a sum k bigger, larger from 0, some amplitude, which I will denote as kk. This will be just the definition of these amplitudes. You can read them out from this representation of the EQSU2. And then there is A plus, which is essentially sine gamma times S plus at S. This you can use to define the amplitudes A going from K to K plus 1. You see, now you have sort of a graph of states. Now this is in ancilla space, so I will draw them vertically. So this is the state number 0, state number 1, state number 2, and so on. This is the highest weight state. I wrote it as a lowest state, but anyway. And then there will be some transitions, as you see. These are like kind of ladder operators. This is all kind of trivial, but this is just that, for Hubbard model it becomes less trivial, so it's nice to introduce the language when it's trivial. Okay, so I forgot to complete. This is the transition from state k to k plus 1. And please, you should interrupt me if there is anything unclear. Everything is completely clear, I guess. Okay. Okay, so I simply introduce these amplitudes, which are simply given in terms of these trigonometric functions times, where this S is given in terms of the noise parameter. So everything is explicit. Yeah? This is really, you can do this in Mathematica, you can compute as you like. this is nothing is hidden anywhere. Okay, so, and now, okay, so what, and then I introduce these amplitudes, yeah? And these amplitudes, I attach these amplitudes, so this is a graph, yeah? Graph is now, so I introduce a graph now, which is the set of edges and vertices, and these vertices are 0, 1, 2, and so on, and edges are pairs of neighboring vertices, which is 0, 0, 1, 1, and so on, so they are diagonal, and then there's, okay, and there is k plus 1, which are, and then k plus 1k. So there are 3 types of edges. There is diagonal edge, there is this self-connection, then there is a raising edge, and then there is lowering edge. Yeah? And to each edge I associate an amplitude, and then I will write, okay, I think I will start erasing stuff. So then this square root of the density matrix, I can now write in terms of a sum, which goes over all walks of this graph, which start at the origin being the highest weight state, or this endpoint of the semi-infinite graph, and in n steps arrive back to the origin. So let me denote this set of edges, E1, E2 to En, being a member of the set of all walks, which at n steps, so this script W will be the set of all walks, which starting at this node end up in the other node in exactly n steps. And so these are just EA1, AE2 to AEN. Okay, this is the amplitude, and then there is the operator in physical space, and the operator can be given in terms of a tensor product of some operators in simple spin space, which are attached to each edge. So that means that I will define something which I call an index function, omega, which associates to each edge an element in the matrix space of 2 by 2 matrices. So that is a local physical operator. Namely, omega of diagonal edges will be sigma 0, omega of k plus 1 edges, that is raising edges, will be sigma plus, and omega of k minus 1 will be sigma minus. So this will be a plus, and this will be a minus. Yeah. And now I have simple selection rules of which terms can exist here or which terms cannot exist. Namely, I always have to start with a plus, which means that I always have to have a plus to the left, sigma plus to the left of sigma minus, which is the Koleski property, which means that that you cannot have anything with, because this is exactly the matrix element of the many-body operator S, and yeah. So all these selection rules which come from the structure of the graph tells you the structure of this matrix. So first of all, it's upper triangular. Second of all diagonal elements are identical, which means that this matrix is completely, the spectrum of this matrix is completely boring. It has just one value, but its Jordan structure is non-trivial. But its singular values, of course, are connected to the eigenvalues of rho. By the way, this also implies that the density matrix of the steady state is full rank, because all eigenvalues of all diagonal, the square root, so no, this is not the object that I had in mind, this object. The square root of density operator, is a full rank operator, so the density operator itself is a full rank operator. I'm sorry for a bit obscure notation. You should keep in mind that different indices mean different symbols. Okay, so is it clear? Some question? Yeah. So that should be clear, I guess. This is just everything should be explicit. Yeah.
So this is an entirely explicit solution for a non-equilibrium steady state for this particular.
Right, for the interacting system.
So have you compared it to what people get in other contexts by using?
Yes. I tell you about it. I hope I have time. So this is the main course, so maybe I skip it at the expense of skipping the results. Go to that. Anyway, but sorry. Okay, so yeah, that's actually. So there are a couple of issues. So let me try to tell you about a spin-off project. Spin-off project, which has to do with relating this to what people have observed in looking at non-equilibrium dynamics of the XXZ chain. So, okay, you may wonder, there's one thing which you can do directly. You can solve Limnat equations of this sort. Once you solve the system exactly, you don't have to solve it numerically, but you can compare with numerical solutions and you will find nice agreement. But this is not what you want because, you may wonder whether this very naive and very simplistic type of quantum master equation has anything to do with reality. So, and then it turns out that anyway, this is kind of interesting. And for example, why is it interesting? Because this gives us a new set of constants of motion. We have learned, the Giffers talk today, we have learned about how important are constants of motion, local constants of motion, local integrals of motion, local conserved operators. Now, this model has been, I mean, you know, it appeared 3 years ago, this model has been beaten to death. I mean, everybody saw that, I mean, probably every expert saw that he understood everything about concepts of motion of this model. And then, you know, the claim I would like to make that maybe this is not totally true, that there are concepts of motion which are not exactly local, but they are what I would call a pseudo-local or quasi-local. Still, I'm kind of frustrated between the use of these two adjectives, I'm sorry. But because they are not, well, I mean, okay, but I don't want to go into this discussion now, but anyway, they are, for all practical purposes, local enough. I mean, practical meaning that you can estimate important transport coefficients of linear response properties of the model, like Drude weights, which describe, let's say, DC conductivity, divergence of DC conductivity of this model. So, I mean, in this critical strip, I mean, there is, maybe I should tell just briefly what is the idea there. I mean, for delta less than 1, that is for gamma being real, there has been mounting numerical evidence that the spin conductivity, the spin current, that is the spin conductivity at high temperature diverges for this model. That is, there is a finite Drude weight, which is related to the conductivity by, you know, there could be in principle a peak at omega equal to 0. This peak has a weight which is called Drude weight, and then there is the rest which is called the regularized conductivity. So this is the real part of the conductivity, this is the regularized conductivity. So there was a lot of discussion in condensed matter community about this Drude weight, and there's been a lot of numerics, and there were different kind of claims that either this guy goes to 0 or it stays finite. Namely, there was inequalities people used in terms of conserved quantities, and these inequalities were exhausting all conserved quantities, and still the lower bound on this guy was 0, which means that if there's nothing else than this, then the best claim would be that this Drude weight should eventually go to 0, even though this was not shown by numerical experiments using quite sophisticated techniques like the MRG. So now I just want to, you know, spend 5 minutes on showing how the solution of this very abstract Lindblad-driven model tells you something new about it. So the point is that you can produce new conserved quasi-local charges. What does it mean? Okay, I have to be brief and only very sketchy about it. But I mean, the key point in this model is there is a particle-hole symmetry, or in the spin language, it should be called a spin-flip symmetry. So there is an operator, let me call it P, which is the product of sigma x at all sides, which is a spin-flip of each spin at each physical site, right? And now this guy commutes with the Hamiltonian. It also commutes with all known conserved quantities. Let's call them Q sub j. Because all these conserved quantities come from a transfer matrix of algebraic beta Ansatz technology. And this transfer matrix, let's call it little tau, which is a function still of some spectral parameter, is essentially written in terms of the same Lax matrix. Okay, now I'm calling a spectral parameter lambda, but never mind, maybe I can call it phi still. And then this spin should be 1/2. So you should consider fundamental representation. If you consider fundamental representation, of course, then fundamental representation is 2 by 2. Then you take a tensor product to power n. So you take a monodromy, and then you take a trace of monodromy, and this is the transfer matrix. And then you take a logarithmic derivative of the transfer matrix at a particular point. You can show these are local operators, and that's it. But the problem is that these guys all commute with this parity operator, this spin-flip operator. So anything you derive from them also commutes with spin-flip operator. The problem is that the current anti-commutes. So if you take a spin current, so let me just define a spin current briefly. So in this language, so if you take this guy, then you apply, product with product of sigma x, you find that it is minus this guy times this. No? So anything you do at infinite temperature has zero overlap, with the spin current. So everything which is related to the transfer matrix of the fundamental representation of beta Ansatz has zero overlap with the spin current. So what you have to do, and this approach shows you what to do. And still, of course, at the end of the day, you want to have something which is quite local. Yeah? Quite local meaning that it's enough local, meaning that you can define some norm of the operator which is extensive quantity. And that's enough. Okay, so just so let me define now something which you could consider as a non-Hermitian transfer matrix. So using this complex spin representation, you can define this guy, but this guy lives in an infinite dimensional Zilla space, so you should not use a trace, because trace would not exist. So you should use highest weight representation, and you should use highest weight state. Now this guy does not exactly commute with the Hamiltonian. First of all, it commutes with itself. So you can show that these guys form a commuting set of quantities. I mean, this is a continuum family depending continuously on two parameters, S and phi, both complex. These guys are commuting among themselves, but they are not quite commuting with the Hamiltonian. That's the problem. Because you don't have the trace here, so there is a problem with the boundary. Anyway, Hamiltonian is an open system, it's an open chain, it's not periodic chain, so you have to worry about what happens in the boundary. So, and then the magic happens that if you define the following operator, which I call Z sub n, but what's nice about this guy is that it does not commute with the parity operator, but if you apply this parity operator from the left, it is the same as if you apply it from the right and transpose this operator T. So this guy is not self-joint, neither symmetric matrix in physical space. It is non-Hermitian. That's the when you go to non-equilibrium, you should worry about everything start becoming non-Hermitian, and all representations of groups should be non-unit. I mean, need not to be unitary anymore. So you should consider non-unitary representations. And this is what you get. Yeah. So you have this P which produces this W transpose. Yeah? And so, since W and W transpose are two independent operators, and they also commute, this guy commutes with W transpose, you can form out of W and W transpose, let's say, anti-Hermitian combination, and you call this, okay, this depends on several parameters, so I will just define what I mean. So, I mean, that's just the crux of the tricks is here, so I just want to, and then finish, because, I mean, I will finish with this and go to the dessert. But just, I try to just be a little bit explicit on this. So the claim is, okay, this guy is non-local. But the magic happens when you take a complex spin parameter to zero, this is a complex spin parameter, so you can put it to zero. At zero, there is a scalar. Scalar is boring. But you expand your transfer matrix, your generalized non-Hermitian transfer matrix, around as equal to zero and take the first term. The first term happens to be quasi-local operator in the sense that, so this guy doesn't depend on spin, sorry. This just depends on one continuous parameter. So, okay, just take a equal guy. So this is just the Frobenius norm, if you want, of this operator. And this is something which goes like over n of n. And that's enough for you. Then you can use these so-called Mazur bounds to bound the Drude weight, and you find. Actually, what's nice is that you find, if you explore really the full set of these guys, and there's a set which is simply a strip in complex plane for which these guys exist and they are quasi-local. So I don't want to go into that, but I mean, there is a kind of nice set, and then you can solve, you can optimize the bound within all these guys in the set. It amounts to solve some Fredholm integral equations, and then you end up with the result which is equivalent to one of the beta results which was obtained by Zotos and then by Klumper at particular values of gamma, which is pi over m. So it agrees with beta ansatz. But at this particular value of points, but this result applies to any commensurate value of the anisotropy. So it goes beyond that. Okay, that's sort of Yeah, I think I still have a couple of minutes, maybe 10 minutes or so.
So excuse me, what does it mean? This O of n, is it quasi-local?
Right, this is what I would define as quasi-local. So you have an operator whose Frobenius norm is extensive. So this operator is a sum of quasi-local guys, of guys which are localized, not on finite support, but they can be written as sums of operators on larger and larger support with smaller and smaller norm. But at the end of the day, you should worry only about this extensivity property. So these are translation invariant sums, essentially. I mean, okay, I didn't say anything about what happens at the boundary. There are terms at the boundary which remain, which are only local. That's again the point. They are only local, sitting only locally at the boundary. So when you do, then you have to use some Lieb-Robinson boundary to show that they are benign when you address the, let's say, the Kubo formula. But this really can be.
And what is the importance of this, having these conserved quantities? These are conserved quantities.
These are conserved quantities. Yes, I mean they can be
even in the case of non-equilibrium.
Yeah, right. They can be used to rigorously bound, let's say, the Drude weight, some ballistic transport coefficient from below.
And all the other ones don't work because.
Only other ones don't work because of the symmetry, because of the positive parity symmetry. And these guys have negative parity, the same as the current. And this is not special to the XXZ model. I mean, there are many models for which the same, like the Hubbard model has the same property. So I have no time now to go into Hubbard model. I've just sketched it very briefly. I will just try to draw a walking graph state for the Hubbard model because it's kind of sexy, but then I will conclude. So, is there any other question maybe before urgently on the XXZ?
Sorry, so is the bond you find for the Drude weight is a function of temperature, or is that just...
No, this is the infinite temperature. This is the Ring order of infinite temperature expansion.
That you can get it at any time?
It could be possible to apply this for finite temperature, but then I don't know how to do anything exactly. So then you should maybe use again some DMRG, to take this as an input and then do some DMRG to estimate this. Because then you have to do these Kubo-Mori products with these guys. So add some finite beta and then, I don't know. I mean, it should be worthwhile to do, but it's beyond what can be done by pencil and paper and Mathematica.
Sorry, what does the temperature mean?
There is, I mean, this here beta is equal to 0, right? I mean, beta is going to 0, from above. So this is leading order in expansion, in high temperature expansion. So there is no temperature here. I mean, this is infinite temperature. Yeah? I mean, this connects to infinite temperature linear response. And finite temperature would be more difficult, as I just explained. Okay, so let me just go in 5 minutes to the first dessert. And then sorry. I mean, there's a whole thing I have to skip. So, I mean, now I can make sort of a poll. I mean, either I say something about computing observables, because I didn't say anything about computing observables, or I go to the Hubbard model. I don't know. It's
Dessert. You promised dessert.
dessert. Okay. So I skip computing observables, but anyway, it should be obvious for anyone who have seen. I mean, there was this tensor ladder. So anyway. Forget about observables. I mean, it's straightforward to compute. Yeah, one can compute currents and magnetization profiles. Okay, just forget it. So now let's go to Hubbard. So, okay, I try to be very brief. So let me just, I mean, you take this rather standard spin ladder formulation of the Hubbard model. So two spins of electrons you represent as two species of spins, sigma and tau spins. That's emission conjugate. Plus, here I will call the interaction as little u over 4. I mean, it doesn't really matter because I will not show you any explicit results for the amplitudes, which you can easily find in the paper. Let's just... So this is a Hubbard model. I mean, it's like a spin ladder. Now, I produce 4 Lindblad channels for the left boundary. I will not discriminate spin up and spin down electrons, so this will be like a charge driving. From the left, I will inject electrons of both spins. From the right, I will take them out. Sigma n minus, tau n minus. And again, magically it happens that this factorization works, where again this Sn is a Cholesky factor, so there is again it solves a kind of defining relation which I will not even attempt to write out. But let me just write the walking graph representation of Sn. So there is a graph which I will maybe draw on this board, which is now a planar graph. But not quite planar. I mean, it's a quasi-linear graph, but it can be nicely written in a plane. Which you can think of by concatenating squares, and you denote nodes of the graph as diagonal nodes. This one you call 0, and this is the highest weight node. Then this guy is 1, 2, 3, 4, and so on. And then you have these off-diagonal nodes, which the ones to the left of the diagonal I will call 1/2 minus, because 1/2 because it's between 0 and 1, 3/2 minus, 5/2 minus, 7/2 minus. And then the guys on the other side of the diagonal I will call 1/2 plus, 3/2 plus, 5/2 plus, 7/2 plus, yeah? And so on and so forth. And then there are connections. Then I will just make out of, to be able to more compactly express what this index function does, I will color some nodes. I will take these nodes, every other set nodes, I will take them as black. So there will be black and white nodes. And on diagonal, these nodes will be black-white. And then there are transitions. And then there are transitions on the edges of the square and on the diagonals. So all these lines, this is directed graph, but I will not plot the arrows. So each pair of nodes which are connected in both ways. And then there are also diagonal self-connections. And these diagonal nodes have self-multiplicity too. So there are two operators associated to the self-connection here. So, just there is a graph, which is the set of edges and nodes, which are just vertices, which are just plotted. And furthermore, in principle, it's possible. And now the idea is just, there is a matrix product operator for the S operator, which, I will not even write out. But the matrix S, the defining matrices A have infinite bond dimension. So the question is how to organize the structure of this underlying space. And and this can be, so the ancilla space, let's say, is a direct sum of local spaces which belong to vertices of the graph. And these local spaces for the half integer vertices, for off-diagonal vertices, k minus 1/2 plus minus, are simply scalars. And the Hilbert spaces for diagonal vertices are two-dimensional. So in principle, there could be more than one-dimensional local space, but it's finite dimensional. So then you have amplitudes. But these amplitudes are, when they go from scalar to scalar, they are complex numbers. But they go from scalar to spinor, they are two vectors. They are rows or columns. Yeah? But anyway, so I assign for each pair, for each edge, which is a pair of nodes, I assign an amplitude AE, which I will not write out. You can imagine it's not. They look quite simple. They are linear functions of epsilon. They are linear functions of k, and then there are some sign factors, some stuff. But they are kind of simple. Yeah? And then at the end of the day, you simply write a tensor. This guy again very easily. So this is a vector of edges. This is a walk. So the square root of density matrix is again a sum of all walks, starting from node 0 of this graph. And then this index function can be understood. So this index function can be understood quite nicely from the diagram of the graph. essentially this B is sort of a component of the connection. If connection is vertical, then only B2, which is the vertical component, is plus if it goes up, it's minus if it goes down, and if it's either 0 or Z, if it stays the same. And then the color of the node determines whether it's 0 or Z. When you connect black nodes, it's Z. When you connect white nodes, it's 0. So it's a nice, I mean, it's a clear coding. Okay, now, of course, there is a question how this coding connects to some Young-Baxter structure, and that's completely open. So for this, I would like to conclude, and thank you for your attention.
Questions?
Yes. I understand right that if you do that on a finite lattice, the dimension is not infinity, you can just cut it at n, or
Right.
these ladder operators.
Right,
So
right.
it scales linearly in
Right,
the system
right,
size.
right,
these-
right, right. So if there would be some entropy, this would scale as log n, yeah, because the bond dimension is. I mean, if you define some sort of operator entropy for these
You
objects,
said that they have full, okay, some
the Schmidt rank
The Schmidt rank
is
is
n,
what?
is n over 2. I mean, here for the Hubbard is 2 times n because it's a package of 4 states for each side. That is boxes. Now, if you allow me just a minute, I mean, the second dessert, which I had to skip, is much more interesting because there, the Ancilla space is generated by 3 degrees of freedom. This you could think of as quasi 1 degree of freedom, right? This is like, it's like quasi 1D graph, so it's 1 degree of freedom behind. It's like a 1 boson plus some spin in this direction. But for a Lie-Sutherland model, you have actually 2 bosons and a complex spin. That is a 3 infinite degrees of freedom. So the graph is essentially part of 3-dimensional lattice and a full lattice. So there's no, which can be again written explicitly and.
And what effect does it have on the entanglement, on this operator entropy?
Right, it affects the stuff to the point that we are not unable to compute observables by not knowing anything more about the solution. So, I mean, then you can plug the solution to the computer and you can go to n equal to 10 because the things explode. It goes to, I mean, it's polynomial complexity, but it goes to n to power 6. I mean, the transfer matrix, because there are 3 degrees of freedom per side. So for the S operator, you go like n cubed, but for the transfer matrix, you have to double it. So you go like n to the power 6, and you are dead after n equal to 10. So you have to have an extra insight to compute observables there.
And so that means actually that your mutual information is bounded by something like log of n. The mutual information in
Right.
your fixed point. Is that something that is generic for all these non-equilibrium processes?
It's generic for this. I mean, I think it's generic for these exact solutions. I mean, for the integrable. I would call this integrable non-equilibrium density operators. And they are probably very different than generic density operators. Now, if you have a non-equilibrium system, I mean, non-integral system, if you break, let's say if you have parameter in the Hamiltonian, but you should break integrability. I mean, it's a good question what happens.
So this would be the analog of an area law, basically.
No, it's possible. I mean, there's still some sort of area law. I mean, based on experience we had with Michael Hinderich some years ago when we tried the first DMRG code on this. I mean, it looks like there is still some sort of area law, but it also seems that there are transitions to cases where there is no area law. So it could be that there are some phase transitions.
Any other question? If not, are we coming back at 4? Is that what we do? 4 o'clock.
Yes.
Okay. So let's meet again at 4. And first, let's thank the speakers again.